This talk is sponsored by Central Virginia Node of Commonwealth Cyber Initiative, and CCI is a state program establishing Virginia as a global center of excellence in cybersecurity research through supporting research, workforce development, and innovation at the intersection between cybersecurity, autonomous systems, and intelligence. And each year, CCI and CVN sponsor research and experiential learning projects. And today's speaker is a recipient of that funding. We have Dr. Kostadin Damevski, and he is an associate professor in the Department of Computer Science at Virginia Commonwealth University School of Engineering. And he has a specialized focus in software maintenance and evolution. And his research spans a broad spectrum encompassing mobile apps, high-performance computing, and industrial software systems. His impactful work, supported by renowned entities such as NSF, DARPA, and DOE, as well as industry leaders like Google and ABB, reflect his expertise in the field. At the helm of the Software Improvement Lab at VCU, Dr. Damevski also serves as the associate editor for the IEEE Software. Today, he will provide valuable insights to the voice control and motion planning of smart UAVs for public safety, shedding light on the challenges of introducing UAVs to enhance public safety in dynamic urban environments. Enjoy this presentation and be sure to join the Q&A session afterwards.
Thank you very much, Zafar, for the introduction, and thank you for CCI-CVN for the invitation to speak. And so this is, as you mentioned, a CCI-CVN funded project for the last year, entitled Voice Control and Motion Planning of Smart UAVs for Public Safety. It's a collaboration between myself at VCU, Dr. Nicola Bezzo at University of Virginia, and Dr. Ju Wang at Virginia State University. The vision of this project is that we would like to enable public safety officers to use UAVs, which are, unmanned autonomous vehicles, or commonly known as drones, in their day-to-day work. So our idea is that a public safety officer would be able to command the drone using voice, rather than having to use a more complicated, commanding interface where they would have to, fly the drone, where they would have to give their full attention to flying the drone. And then the other part of it is that the drone would have to navigate a city environment, which is complex and dynamic. So really, the challenges of the research are on two sides. So there are the challenges related to commanding the drone, and there are challenges related to flying the drone. I should be clear that my work is on the side of commanding the drone, and the collaborators at University of Virginia and Virginia State University are the ones leading the effort of navigating the complex city environment with UAVs. So our research challenge was kind of laid out as having the public safety officer say something like, follow the person in the yellow shirt to the UAV, and the UAV being able to then navigate the city environment and be able to accomplish this task. So the idea is that then the public safety officer would also be free to do other activities while the drone is helping and assisting him. So it required a conversational or spoken interface for commanding the UAV, which again combines technique from human-computer interaction, because we would like to understand what would be the best way for that public safety officer to express these commands, and it would be a natural way to interact with the UAV, as well as techniques from natural language processing and voice recognition, which are required in order to handle the fact that this, to translate the voice commands into actual commands for the UAV, as well as to handle, the noise, background noise, a complex environment where this public safety officer may be communicating their commands. On the other side, the city environment is dynamic, consists of moving vehicles, humans. There are obstacles like trees or power lines and such. So it really requires and it challenges a UAV in order to be able to navigate that environment autonomously. The goal here, obviously, is to do that autonomously without any human control, which requires techniques from robotics, techniques from image processing, techniques from path planning and AI in order to accomplish these tasks. So this was sort of the high-level vision that we laid out for this project. So the high-level research goals, again, are the public safety officers should be able to use the UAVs in their day-to-day work without having a dedicated person that is going to just be in charge of flying the drone. And then we want to use high-level, voice commands that enable a public officer to, communicate very naturally to the UAV their, requests, and the UAV would follow these. And then the UAV would be autonomously navigating the city environment without, needing human intervention in order to navigate various obstacles. So this is sort of the big picture idea. So this is the outline of the talk I have planned today. So I discussed kind of the vision of this talk. Next, I'd like to talk about the shorter term goals. So this was a 1-year project. So we translated that vision into specific goals that we could accomplish within 1 year. And then the results of those goals, meaning what we were able to actually accomplish. And we have a couple of demos that I can show you. And then the next steps, meaning the next kind of spun off research ideas that have come out of this project, which are related to voice-based UAV programming. We can actually get multiple commands from voice, and then having a combination of multi-UAVs and multi-humans on reconnaissance missions. So I'll talk about those kinds of as future work or next steps that we're interested in to follow on this project with. Okay, so this high-level vision that I just described, we distilled it into some shorter-term 1-year goals by using a set of assumptions or simplifications, if you will. So we, first of all, simplified the task by considering only commands related to a single building, right? So the commands would not, have to do with, like follow the person with the yellow shirt, but rather something related to a specific building, such as monitor a building or, monitor a particular entrance of a building or taking pictures or a variety of things related to a single building in a city. We also try to utilize off-the-shelf AI and machine learning models, because training the complicated ones or fine-tuning ones to the specific tasks would have required more time and energy. So we use off-the-shelf models wherever we could. And we started off working with a simulated environment rather than having the UAV actually navigate a city or a building, because there are lots of difficulties with flying a UAV related to permitting issues. First of all, although we did do some experiments at University of Virginia, because they do have a dedicated small airport in Dr. Betzo's lab, where we could test some of these things in a limited way there. So we started off with a set of commands that we thought would be useful to a public safety officer in commandeering a UAV. So we, again, specific to the task of exploring a particular building. So we devised 3 commands for exploring buildings. The explore command, which the idea was, explore or look around a particular building. So maybe take a circle around a particular building and scan all different angles. Take a picture command. We wanted to tell the UAV to take a picture of, let's say, the backside of a building and communicate that to the public safety officer. Or just monitor, which was more of a loitering kind of idea, where the UAV would just wait at a particular side of the building, maybe at a side entrance, and just wait for activity that way. We also introduced a set of commands needed for safety, like stop what you're doing, take off, land, come back, and a set of commands that for small kind of runtime feedback, like go left, go right, go up, go down, get closer. So we had basically, in this way, introduced about a dozen or so commands that we wanted the UAV to recognize and to be able to translate into actions. So to give more examples, so the explore UAV command could look like this, where we would say, can you explore the 2nd floor of the greenhouse, right? Or look around the top floor of the house on Main Street, right? So, I'm sorry, 601 West Main Street. So, or go and look inside the attic of the large house across the street, right? So given these sort of commands we wanted to recognize, we also wanted to recognize certain entities that we would need to translate into, to provide to the UAV in order to be able to navigate. So for example, the floor and the building were entities that we needed to pull out of this communication that are necessary for the UAV to understand. So in other words, in addition to understanding that this command would require the UAV to explore something, we would need these entities in order to know what to explore or how to explore it. So the take picture UAV command, here's a few examples of that. For example, take a picture inside the nearby blue house, or take several pictures of the location that you're currently at, or take a picture of the second floor of the house at 302 Busy Street. And again, there's a set of entities that are required in the context of this command that would be necessary for the UAV to perform its tasks. So our first attempt, the first thing we set out to do with respect to recognizing the commands was to use these fixed response conversational interfaces, right? So this is a set of tools that are already available for these kinds of actions. And we happen to utilize a very popular toolkit called the RASA toolkit. And the idea is that we provide to this toolkit a set of data explaining the specific types of commands and explain the particular structure of the conversation, specify the specific machine learning models and specific pre-processing we would like to do, and the toolkit would be then able to integrate all of these things into a solution. And it required, however, to create a training set for each command and to supply that, and that way the toolkit would be able to recognize each command individually. So this was our first attempt. We realized that there were some challenges here because there were many different formulations of commands that people may express, which really translated to us having to provide a larger training set in order to achieve a higher accuracy. So it wasn't sufficient to, for example, provide a training set of a couple of dozen instances of the explore command. We needed a much larger training set of, let's say, hundreds and hundreds of these commands in order to be able to recognize all the different ways that people would express, or public safety officers would express this command. At the same time, actually, kind of roughly at the time when we were struggling with this task, ChatGPT came out. So that immediately caught our attention as a model that maybe we could utilize with less training data. So we translated to generative AI and to OpenAI's models in order to attempt to utilize these large, pre-built models, pre-trained models by OpenAI in order to get to higher accuracy. So this is what worked a lot better. So we set out this pipeline, right? So I show this in the kind of the top part of this picture, where the human would issue voice commands. They would go to a specific model called Whisper, which would do voice to text recognition, right? So it would translate voice to text. And we found this model to be excellent. It really didn't require us to do much except for integrate with the model. So we didn't need to provide any customization. It just worked really nicely. Then the text would be fed into OpenAI's ChatGPT model. This one, we used few shot prompting. So we actually provided it with about a dozen or maybe 24 examples of each command in order to kind of train it in order to recognize the different commands and to be able to extract all the entities we care about. Unlike the previous generation, the few shot prompting was sufficient. So it was sufficient to provide relatively small amount of examples, and the model was able to generalize pretty well from that. So we're able to run a number of tests, and we're pretty satisfied with the results that it had in recognizing the commands. The output of this, which was kind of at this point structured data, was fed through a web service to the robot operating system, which would then be able to commandeer the UAV, right? So we wrote a web service as well as some logic in the robot operating system, of course, in order to work through the different assumptions that we had about flying the UAV. So so this was pretty good solution. Of course, the slight negative aspect is that given the fact that we were using these off-the-shelf tools through a web interface as services, we had to pay a small fee every time per interaction, essentially, per interaction with ChatGPT and per interaction with Whisper, but very small fee, of course. So we have this prototype, and I'm going to show a small video that the students have recorded of actually interacting with the full prototype, the pipeline that I showed in the previous slide, going from voice commands to actually flying the UAV and performing tasks in simulation. So the interface looks a little bit like this. So this is just the voice part of the interface. We also have the simulation environment, but you can see kind of at the top of this, we would provide the URL to the robot operating system, so to the UAV itself. So we could specify dynamically in a text box where the UAV is located or where the UAV is actually listening. There was a button. You see the button for start voice command, which you would click, and then you could speak. And this is a web application that you could run on any browser. It would show you some output, as you see in the operator box below, of what actually you have told the UAV, so kind of as it's recognized the command. And then it would provide some feedback, as you see this like Roger that, etc., giving you feedback of what the UAV is currently doing. So this would be where the UAV would actually be communicating its current actions back through the interface to the public safety officer. So I have a small video that I'm going to play right now. Again, this is that the students had recorded of the full pipeline working, and hopefully that will give you a better sense of how this all looks. So here it goes.
Off. So take off. So take off. Ah, we're at wow, very nice, very nice. Okay.
Yeah.
So then go to the house. Okay.
I think I already coded it.
So let's do go to the house. Okay, cool. That's funny. I didn't really know, but still did it. Okay, on the way. And take a picture of the house. Nice. Yep. So we can click here. Now, in the simulator, it's just a black and white picture. But took a picture of the house. Oh. Lands. Take it off. So take off. So take off. Go to the playground. Kind of coded it up to be a little slower. Yep. Yep. And then, yeah, so he goes to the playgrounds. And perspective's kind of wonky here, but yeah, it's kind of like stopping more or less on the playgrounds. We say, take a picture of the playgrounds. Should take a photo. And boom, there's the playgrounds.
Yeah, so that's concludes it. So that hopefully gives you a little bit of a sense of how this worked, where we implemented both the conversational interface, which is again one website or a web application that communicates underneath to the simulation, implemented in ROS and robot operating system, and also all the navigation parts, and all of that stuff is handled within the code written in ROS. So going forward, oops, sorry. Okay. So again, we've implemented several of the commands that we set out to do. We've started working a bit on doing some experiments outside of simulation. So we do have a short demo where, we're doing something, as I mentioned, at University of Virginia, their small airport. We are still working on adding additional commands, and we're still working on, conducting a user study with public safety personnel in order to better understand what specifically they have in mind. What are the goals of their that they would like to have? So basically, how they could use this prototype in order to better understand where they would like to improve and what specific new commands they would like to add. So given this set of accomplishments in this one-year project, we set out to do a couple of additional projects that kind of spun off from this collaboration that we had with University of Virginia, Virginia State University. The goal was, again, to look for potential for new things that we could explore, as well as new ideas that we could garner funding from. So we created two ideas. One is a voice-based programming interface, where instead of a single command, which is what we had up to this point, we could now have a set of command or a set of steps, essentially a small program being generated through the voice interface. And then we had an idea of using multiple UAVs and multiple humans essentially interacting as a group to explore a complicated environment in a type of a reconnaissance mission. So I will talk about both of these briefly, one by the other, and we actually have a small demo for the first one. So for the voice-based UAV programming, we're, again, trying to go forward from just a single command to the UAV to something that we could generate a full program or a small program, a sequence of steps that a UAV could perform. Instead of a UAV, however, here, we changed the focus a little bit for this project. And we use a robot, a one-armed robot that we have in our lab. So we have this robot on the side, this picture of this GOFA robot. We have two of them in our lab. It's basically a single-armed collaborative robot. So it's meant to work alongside humans. It's meant to be easily programmed by humans and easily controlled. So if it bumps into a human, it's able to detect that and navigate around that. And so I can show you what we've kind of created in that way. So we built a small prototype demo for using this GOFA robot. We have kind of a sandbox environment for this that's kind of simplified, but meant to illustrate the main points. So on the right side, you kind of see what the robot is doing, essentially as a simulation, where the arm of the robot is in the center of this. And A, B, C, and D are different locations that the robot would like to go to. And also there are boxes, A, B, C, and D, that the robot should move maybe to those specific locations. That would be a task that the robot could perform. On the left side of the screen, you see these blocks that essentially can be dragged onto the middle of the screen in order to create the program. So that's sort of a very basic programming environment, sort of similar to what, to like Scratch or other ways that people learn how to program. So it's meant to be very easy to use and meant to be performed by people who are not trained in programming. So here's our little demo on that. So I'll play that next.
Hey, this is a demo for LLMS for single arm robot control. In order to compile the code, we can first download live server from the VS Code extensions. Once it's downloaded, you can see a go live button at the bottom right corner. And once you click on it, it brings you to this page where you can select sandbox environment. And this is the environment that we have been working with. Record robot instruction is the functionality that we have been working on last semester. Once you click on it, it brings you to this default view workstation. We're still working on the UI, but what this functionality does is it allows the users to record their instructions, which then will be converted into a text that gets fed into a GPT engine. Then the system gets the code from GPT and transfer it to the roadblocks. The user gets to see the roadblocks in the preview station to make sure that this is the type of action that they want their robots to execute. Here we can give a simple instruction such as move to location test to pick up the object, and then move to location test 2 to release the object. Yes, once you review the blocks and see this is the type of action that you want, and then you can click on yes button, that it will bring it to the home page, and then you can attach it to the first roadblocks, and then click on start program. And this is the end of the demo. Thank you. Hey, this is a demo for.
Okay. So just to wrap that up, so the student showed how using a voice interface, it's a similar pipeline to what I showed for controlling the UAV. It's fed through Whisper and through ChatGPT in order to translate the voice commands into a sequence of steps that then could be executed by this particular one-armed robot. So that's one future direction that we've been exploring. Another one is shown in this slide, where we're looking at multi-UAV, multi-human reconnaissance missions. So this is, we're considering DoD, Department of Defense applications. And something that they were particularly interested in was enabling a group of soldiers to navigate a dense forest with the help of UAVs, right? So again, a forest has some of the similar properties as the city environment we discussed at the beginning, because there's a lot of obstacles and there's foliage and things like that that the UAV needs to autonomously navigate around. At the same time, the soldiers don't have the time to actually, use a commanding screen to fly the UAV, and they would like to use this more natural voice interface in order to interact with the UAV. In this scenario, however, we want to have a group of UAVs that are actually able to help a group of soldiers or a group of humans moving through this forest. And the idea is also to use the cover of the forest whenever possible. We're also interested in exploring advanced sensors that would enable the UAV to be harder to detect. And we're interested in, again, using the cover of the forest whenever it's possible, advanced sensors, and then certain high-level commands that would enable to coordinate a group of UAVs, for example, zone defense, or spread out in a particular space, or focus on a particular area, or explore a particular direction. And the scenario we're also interested in is having multiple humans be able to command the UAV, giving specific directions, maybe to an individual UAV or set of UAVs, in order to navigate this area. So this is something that we're in discussion, or we're interested in pursuing with collaborators at the Department of Defense. So again, my talk summary was about a one-year project with funding from the CCI-CVN, whose goal was to create an interface for commanding UAVs for public safety in kind of a city environment. We designed a set of context-specific commands, worked on voice recognition, text understanding, worked on advanced, UAV autonomy, obstacle avoidance types of algorithms. And, we've followed on this project with certain ideas that go forward with, creating, additional steps, so programming the robot or the UAV rather than just a single command, and then also coordinating between a multi-human, multi-UAV environment that I just described. So that's the summary of it. This is the group of researchers that we had. So on the left is our group of people at VCU. In the center, we have Nicola Bezzo and his students at University of Virginia. And we also had help from Dr. Zhu Wang and his group at Virginia State University. Thank you again for your attention, and I'm open for questions.
Did you do anything to handle under-specified commands? For example, if the command was take a picture in the window, but there were multiple windows.
Right, so that's an excellent question. So there's always going to be ambiguity here, right? There's always going to be an issue where, in this case, given the example that you provided, the UAV is going to just go to the nearest window. But if there are multiple windows and that's not the intention of the speaker, that's an issue, right? So we don't have a very good interface for kind of a follow-up questions or sort of conversation with the UAV, right? But that is certainly an area that we could explore, where the UAV may be able to ask, which window do you mean? And then receive like a more specific instructions and when it's an ambiguous command. Thank you very much for the question. And I'm definitely available, and the link to my website is here on the slide. So if anybody has any additional questions, they could feel free to contact me. And my email address will be available through the website.
Thank you so much for taking the time out to do this. We really appreciate it. If there are some more questions, we can go ahead and end this. So I dropped the link in the chat for next week. We have Dr. Linsky coming in, so we'd be really happy if you guys joined us for that. All right. Thank you so much.
Thank you.